Let's talk about something I think many of us have run into with modern AI. It's this really frustrating disconnect, right?
Yeah. You mean having these incredibly powerful models?
Exactly. Models with, hundreds of billions of parameters. They've supposedly read everything.
Uh-huh.
But then you ask for something genuinely hard, like a complex plan, maybe a mathematical proof, or even some nuanced code.
And you get something weak.
Yeah. It feels like a lazy answer, a platitude sometimes. It looks okay on the surface, but it's just strategically
Yeah,
useless.
coherent nonsense at the time.
Right. And if you're building with these tools, you know that feeling, like you're being shortchanged by all that power.
Definitely.
Well, here's the really interesting discovery we're diving into today. And honestly, it could change how we think about using these systems.
Okay. The core idea is
Mm-hmm.
the problem often isn't the model itself. It's how we get the answer out of it, how we sample from it,
Right.
the decoding process.
Yeah, exactly. There's recent research suggesting that the base models, the ones before all the heavy fine-tuning, already have this massive kind of latent reasoning capability.
Mm-hmm. Deep, complex thought potential.
But it's hidden. It gets buried under, the standard way these things generate text, which is often optimized for speed, maybe not for deep accuracy.
And that's the crucial reframing, isn't it? So our mission for this deep dive is really to explain how you unlock that hidden genius. And the key is, this isn't about needing more expensive retraining or setting up complex reinforcement learning pipelines, which can take ages.
Right.
We're focusing on really practical inference time tactics, things you can often do right now.
Just by changing how you ask or how the machine generates the response.
Exactly. Small moves, sometimes just prompt changes, or using slightly different generation settings to get dramatically better, sharper reasoning. We're shifting the focus sort of from the training cost to the execution cost, but making that cost intentional.
Okay, let's unpack this. So for years, the story has been, if you want better reasoning, if you need that step-by-step logic and less of the fuzzy confidence.
You need RLHF.
Yeah.
Reinforcement learning from human feedback. Or training a reward model, lots of fine-tuning. That was the standard playbook.
Yeah. But this research seems to challenge that pretty directly, doesn't it?
It really does. The argument is that many of those reasoning gains we thought came from post-training.
Yeah.
Well, they might actually just be a sampling effect.
A sampling effect, meaning...
Meaning the models weren't necessarily being taught how to reason better during fine-tuning. They were just being kind of forced or guided to show the reasoning paths they already knew more clearly.
Wow, okay. That's a big shift in thinking. It is a profound mental shift. Think about it. If the capability was mostly baked in during pre-training, when the model ingested just, unbelievable amounts of text and data, trillions of tokens,
Then the ability to follow those deep logical rates, it's probably already there. It just gets obscured because standard decoding often takes the easiest, most probable next step. It's a bit short-sighted.
So we stop thinking of reasoning as something we have to create through training.
And start thinking of it as an extraction problem. The base model can likely navigate the complex path. The trick is guiding the generation towards those high-quality routes.
Without crushing the diversity, right? You don't want it to become too narrow.
Exactly. You want to bias it towards coherence, but not make it rigid.
So framing it as extraction, that really changes where you put your effort. Less on the training, more on the inference.
Right. The inference budget becomes key.
Okay, so how does this specific technique work? I think it's sometimes called power-biased sampling, or similar names. What's it actually doing differently at that inference stage?
Yeah, it's definitely more sophisticated than the old trick of just turning down the temperature setting.
Right, which makes it less random, but maybe more repetitive.
Exactly. Lowering temperature only sharpens the choice for the very next word, the next token. It's very local. It doesn't really look ahead.
Okay.
Power-biased sampling and these other related search-based methods, they try to sharpen whole sequences. Think longer term.
How?
Well, imagine normal decoding is like driving using a GPS that only shows the next 10 feet. You'll probably get there, but you might take some weird turns or get stuck in local traps. Power sampling is more like stopping every so often, sending up a drone to check the next few miles. It uses the model's own probability estimates, but looks at the viability of a whole sequence of upcoming steps.
So it's doing little internal checks during generation.
Precisely. It might generate, say, 20 tokens ahead in a few different ways. Then it uses a principled method to see which of those potential futures looks most promising overall, based on the model's own scores. It accepts the better candidate sequence and continues from there.
So you're paying for this internal review with extra compute time during decoding.
That's the trade-off. More compute at inference for more rigorous internal self-correction.
And that seems crucial for complex reasoning, doesn't it? Because the quality of step 1 in a proof depends entirely on whether it allows for a valid step 10 down the line.
Absolutely. It's about global coherence, not just local probability. And just to clarify a term here, this approach helps avoid something called mode collapse.
Ah, right. Where the model gets stuck always giving the same kind of answer.
Exactly. Sometimes after really intense RL training, models can become very rigid. They default to one high probability answer type, even if something more diverse or creative would actually be better. This search method tends to avoid that kind of rigidity.
Okay, that's the mechanism. But the big question, I guess, is, does it work? Do the results justify potentially spending more compute at inference time? Can a training-free decoding trick really hold its own against models that went through hours of RLHF?
Well, the results they're showing are, frankly, pretty striking.
Yeah.
On standard benchmarks for tough tasks, things like math proofs, coding challenges like human eval, complex science problems, the single-shot accuracy you get just from this smarter sampling, it rivals, and in some cases even beats, heavily reinforcement-trained models.
Single-shot accuracy matching RLHF models. Just from changing the decoding, that's a massive statement about the power hidden in the base model.
It is. But here's what might be even more valuable, especially if you're actually building products with this stuff.
Yep.
It keeps the response diversity high. We mentioned avoiding mode collapse. This really does it.
Yeah.
You look at metrics like pass at K.
Which measures how likely you are to get a correct answer if you generate, say, 5 or 10 different attempts.
Exactly. With these methods, those pass at K curves keep climbing nicely. They don't flatten out the way they sometimes do with overtuned models. So you get strong accuracy on the first try, and you get variety if you need multiple options.
That combination, good first shot plus high diversity, that's pretty rare, isn't it? It's incredibly valuable. It means the models are more adaptable, they can handle different topics or unexpected questions better because they haven't been forced into one narrow way of thinking. They travel well, so to speak. Okay, this naturally leads to the elephant in the room. The cost. I mean, you mentioned paying more compute at inference. The research sometimes shows needing, 8 or 9 times the normal token spend for one complex answer? That sounds expensive.
Yeah.
It can be, yes.
So how is that strategically better than, say, spending a few million on training a model really well once and then having cheap, fast inference forever after?
That's the core strategic trade-off, you're right. And you have to weigh the different kinds of costs and risks.
Okay.
Training, especially deep RLHF, is slow. It's very, very expensive. And maybe most importantly, it can be brittle.
Brittle how?
Well, imagine you're working in a very specialized area like, I don't know, specific enterprise legal contracts or some proprietary engineering field. You might not have a perfect data set or a reliable reward signal to train against safely.
Ah, right. The feedback loop is hard to build.
Yeah.
Exactly. That can lead to fragility, where the model works great on the training examples but falls apart on anything slightly new. Reward hacking, overfitting, all those problems. Yeah. This sampling approach, on the other hand, is training free. You don't need a special data set. You don't need a reward model or verifier. You pay for the extra search only when you need it.
Ah, so the cost is dynamic.
Precisely. The strategic advantage is flexibility and immediacy. You can deploy a capable base model today and get high-quality reasoning on demand without the long, risky training cycle.
So for open source users, maybe a good base model plus this kind of decoding can compete with closed, expensive ones.
That seems to be the implication. And for enterprises with private or sensitive data, you can potentially skip that whole complex training pipeline, which is a huge win.
Yeah.
So the big shift is treat inference compute not just as an unavoidable cost, but as a strategic lever, a dial you can turn up or down. Exactly. If the question is simple, low stakes, like summarizing an email, use the fast, cheap default decoding. Save your compute budget.
But if it's high stakes, drafting legal text, generating production code, analyzing a critical report,
then you consciously decide to spend more compute budget at inference time to enable this deeper, more rigorous search. The control stays with you dynamically.
Okay, this is fascinating. But what if you don't have that low-level API access? What if you can't just switch on power bias sampling tomorrow in your system?
Right, that's a practical limitation for many users right now.
Does this whole idea just become theoretical then? Or is there a way to kind of simulate the spirit of this?
Absolutely. The core insight, forcing the model to search more deeply, explore alternatives, critique itself, you can encourage that. using simple prompt patterns. Think of it like a human-operated version of the algorithm.
Ah, using the prompt to guide the search manually.
Exactly. We've got about 5 patterns here that are designed to do just that, to push the model into that deeper internal search and self-review, basically mimicking what the fancy sampling algorithms do under the hood. It's about structuring the conversation for rigor.
Okay, I love practical patterns. Let's hear them. Pattern 1. Pattern 1 is the simplest, maybe the most well-known, but still powerful. The step-by-step mandate. Think step by step. Pretty much, you explicitly instruct the model. Solve this problem step by step. Show each step of your thinking clearly. Then, give the final answer. It forces the reasoning process out into the open, makes hidden assumptions visible. Great for math, logic puzzles, anything with constraints. Makes sense. Pattern 2.
The self-correction loop. This manually creates that internal review cycle we talked about, mimicking the resampling idea.
How do you prompt that?
First, write a draft answer to the prompt. Then, review your own draft. Look specifically for errors, missing logic, or unsupported claims. Finally, provide a corrected, improved, final answer.
So you're explicitly asking it to find flaws in its first attempt.
Yes. It acts as an immediate repair step, often catching weaknesses the model might have otherwise just glossed over.
Okay, pattern 3.
Multiple perspectives. This directly taps into boosting that diversity, getting that pass at K benefit in a single interaction.
Useful for complex problems with maybe more than one solution. Definitely. Think coding, debugging, maybe strategic planning, you ask. Propose 3 distinct approaches to solve this problem. Compare the pros and cons of each approach. Then select the best one, justify your choice, and provide the final answer based on that approach. So you force it to explore different paths before committing.
Exactly. You inject the diversity generation yourself.
Clever. What's pattern 4?
Pattern 4 is expert persona scaffolding. This helps activate relevant knowledge and filter out generic noise by making the model adopt a specific expert stance and declare its principles upfront.
So more than just act like an expert. Yeah, more structured. Try.
Yeah.
You are an expert in specific domain, like, say, contract law or semiconductor physics. Before answering, list the key principles or frameworks you will use to analyze this problem. Then, apply those principles rigorously to generate your answer. Making it state its methodology first.
Right. It forces a kind of structured thinking that often boosts the quality and consistency, especially for complex analysis or summaries.
Okay, and the last one, pattern 5.
Red teaming your own answer. This is absolutely vital for high-stakes stuff, for guarding against that confident-sounding but ultimately flawed output.
So, asking it to critique itself. Yes, specifically asking it to find the weaknesses. The prompt could be, before finalizing your answer or recommendation, list 3 potential weaknesses, risks, or counter-arguments associated with it. Address each of these points directly. Update your final answer if necessary based on this critique. Wow, that forces honesty about blind spots. Crucial for strategy, risk assessment.
Exactly. You're making the model confront its own potential failure modes.
Okay, those 5 patterns make a lot of sense as manual ways to push for better reasoning. Now let's connect this back to the compute budget idea. If you use these patterns, especially the more complex ones,
You're definitely increasing the interaction length and therefore the token count. You have to plan for that. Just like the algorithmic methods scale with search steps, these manual patterns scale with conversational turns and complexity.
right. That research showing 8x or 9x token spend for complex math proofs, that's the upper end of this intensive search, whether algorithmic or manual.
It's a significant investment per answer, absolutely.
But again, an investment you choose to make when the cost of being wrong is high. So, how should teams think about this? How do you map the stakes of a task to the amount of effort or compute or tokens you should invest using these patterns? Is there a guide?
Yeah, we can think in tiers based on reliability needs. For low-stakes tasks, maybe quick email drafts, brainstorming ideas, you probably just use a single pass. Maybe add the step-by-step pattern if structure helps. That's roughly your baseline, 1x token spend. Fast, cheap, often good enough.
Yeah.
Then for high-stakes tasks, think internal reports, moderately complex code, generating initial drafts of important documents. Here you'd want to use maybe the multiple perspectives pattern, force the comparison, maybe add a self-correction loop.
So layering a couple of patterns.
Right, that's pushing you into maybe the 3x to 5x token spend range. You're explicitly trading more tokens for fewer silent errors by forcing that internal debate and review.
Got it. And then for the really critical stuff.
For critical analysis, yeah. Where the output might be customer-facing, go to regulators, inform a major decision.
Where accuracy and robustness are paramount.
Absolutely. Here, you deploy the full arsenal. Use all 5 patterns, maybe even run the generation cycle twice on key parts. This is where you could hit that 5x to 8x token spend, or even more.
And presumably, human review is still essential at this level.
Oh, always. But using these patterns means the input to the human review is vastly more reliable. You've forced the model to exhaust its internal reasoning and self-critique capabilities first. You've bought the highest possible machine-generated reliability.
So pulling it all together, this manual approach gives us a really powerful workflow, doesn't it? It mirrors the logic of the sophisticated sampling research, but anyone can apply it right now. It really does. It's like a new standard operating procedure for getting trustworthy reasoning out of these models. Let's recap it quickly.
State your objective clearly. Very important first step.
Okay.
Generate multiple distinct takes or approaches using that multiple perspectives pattern.
Inject diversity.
Force the model to compare those takes and justify its chosen path. Selection and justification.
Make it commit.
Run a self-correction pass. Make it review its logic, evidence, and completeness.
Internal review.
Red team it. Force it to list and address its own weaknesses and failure modes.
Self-critique.
The goal through all of this is simple, really. You're not trying to change the model's fundamental knowledge or weights. You're changing its search strategy during generation. You're actively directing its thought process. The headline from all this research, then, seems crystal clear. Your base model is probably way smarter than you think.
Yeah, that seems to be the case.
Post-training like RLHF is valuable. It's like a lens that can focus that intelligence. But smarter decoding, smarter search, whether algorithmic or manual, is the essential guide to actually accessing that intelligence. The deep reasoning capability often seems to be baked in already. We just needed better ways to reliably pull it out.
And this really forces us, as users and builders, to stop treating decoding as just the last step, an afterthought.
Absolutely. It's not just a technical detail. It's a strategic surface. It has levers like search depth, diversity, self-critique that can radically change the outcome, often giving you those single-shot gains with high diversity, and crucially, helping avoid the brittleness or mode collapse risk that can come with intensive RL tuning. So if there's one core idea to take away from this deep dive today, maybe it's this. Don't just trust the first answer, especially for important tasks. Definitely not.
The model likely has a better, more reasoned answer inside it somewhere. The real leverage, the fastest wins right now, might come from getting better at using the models we have, not just waiting for bigger ones.
It's a shift from just kind of coaxing answers out towards intentionally directing the model's thought process.
So what does this all mean for you listening? Well, try it. Pick one important, high-stakes task you use AI for this week. Run it through those 5 patterns, especially layering the self-correction and the red teaming.
Measure the difference. See if the quality, the robustness, the reliability improves.
You might just unlock a level of AI reasoning that you technically already paid for when you access that base model. And that feels like a massive, immediate potential gain for almost any workflow.